Hello, welcome to my video on data structures. This is the second video for the array data structure, and we will be motivating several other operations supported by array. Recall the example we had in the last video where you are running an online business. We end up with storing information relating to the items you sell in an array data structure. The information is stored one after another in continuous memory blocks. We have discussed three fundamental array operations in the previous videos. We could access the information of an item given its index of the array. We could insert information for an item at the end of the array, and we can delete an existing item from the array. In this video, we are going to discuss several other array operations. To motivate these operations, consider that we wish to store the items in an array with some order. Nowadays, most of the online retail websites support this feature. For example, you can sort the items by their prices, their customer ratings, or by other features. Let's assume that we wish to store the item based on their customer ratings. In this way, we can quickly locate the item with the highest customer satisfaction and remove items with the lowest customer satisfaction. Now, recall that all the operations we introduced in the last video assumes that the items are not sorted. Would it change those operations if we are dealing with a sorted array now? Remember that when we discussed the operations in the last video, the key idea we kept in mind was that the data elements were stored in continuous blocks. And now, in addition to ensure the elements remain stored in continuous memory blocks after any operation, we further need to ensure that the elements remain sorted. Now, let's see whether the additional constraint would make any changes to the existing operations. The first operation that accesses the information of a given index should not be affected, as it is independent of whether the data is sorted. The second operation that inserts a new data element is affected. This is because we need to make sure that the new data element is inserted into a proper position if we want to keep the data sorted after the insertion. In other words, instead of inserting the new data element at the end of the array, we may need to insert it into an arbitrary location of the array. The last operation that deletes a new data element should stay the same, as deleting elements will not alter the relative orders of the remaining elements. Okay, let's see how should we insert a new element into an arbitrary position I in the array. Since the data elements are stored in continuous memory blocks, we need to move all data elements after the insert position to spare the space for the new element. For example, item n needs to be moved to position n plus 1, item n minus 1 needs to be moved to position n, and so on and so forth. After moving the data, we will insert the new element into the position. Note that the new insert operation may also face the issue of insufficient memory. This is the same as our old insertion operation that simply insert to the end. The solution for this issue is the same as that for the old insertion operation. We find a new place with more memory blocks and move all data to the new place. And we can reduce the frequency of such data move by requesting more space than needed. However, no matter whether we have sufficient memory, the new insert operation will need linear time O(n) to complete, as it will need to move the data to spare the space for the new element anyway. In addition to the change for data insertion, we also want our data structure to support three other operations. They are access the first element, access the last element, and delete the last element. Note that these three operations are there just for convenience, and they make more sense when the data is sorted. For example, we can retrieve the item with the highest customer rating by accessing the first element, and then we can pull the worst item from the shelf by deleting the last element. The implementation of these three operations are trivial, as they are just the special cases for the existing operations. Accessing the first and last element are special cases for the data access operation, and deleting the last element is a special case for deleting a given element. To implement them, we just need to supply proper indexes as parameters to the more general operations. Now, I want to briefly discuss the pros and cons of storing data elements sorted and unsorted. The advantage of keeping the data elements sorted is that finding an element becomes easier. For example, we can easily get the maximum and minimum elements of the data. We can further use a faster search algorithm called binary search to locate the element with any value in O log n time, where n is the number of items in the array. While the same operation on an unsorted array would take linear time O(n). I will explain the idea with a very brief description of the binary search algorithm. Imagine we have an array with sorted customer ratings, and we want to find the item with a customer rating 4.0. The binary search algorithm always checks the middle element of a plausible range, which corresponds to the positions where our target may occur. At first, the element we want to search may locate at any position, so the entire array is the plausible range. In this case, we start with checking the middle element 3.5. We compare 3.5 with our target 4.0 and notice that the middle element is smaller than what we want to find. Because the array is sorted, if 4.0 indeed exists in the array, then it must locate at positions after 3.5. Then, the new plausible range is now between 4.0 and 4.8. At the second iteration of the binary search algorithm, we check the middle element of the new plausible range, that is, 4.6. We compare 4.6 with our target 4.0 and conclude that the target, if exists, must locate before 4.6. Then, the new plausible range becomes just 4.0. We compare that with our target and then claim we have found the element. Since the plausible range is reduced by half each time, the time complexity of the binary search algorithm is O log n. However, if we do not keep the elements sorted, then we have to check each element. This is because we cannot use any comparison result to effectively reduce the plausible range, and we can easily conclude that this process takes linear time. Having discussed the advantages for storing the data elements sorted, now let's see its disadvantages, which is the extra effort we need to pay to keep the elements sorted. Recall the new insertion operation we have just discussed. To spare the space for the new data, it has to move all data after the insertion position. Therefore, no matter whether we have sufficient memory to hold the new data, it will take linear time to complete. On the other hand, the insertion for unsorted data, which just inserted data to the end of the array, only takes constant time when memory is sufficient. At last, I want to clarify that whether the data elements are stored unsorted or sorted is a choice of the user, not the array data structure. In other words, we usually do not take unsorted array and sorted array as two different data structures. Instead, we just have a single array data structure that offers interfaces to support both unsorted and sorted data storage. It is the user's responsibility to apply the proper operations on the data if she or he wants to store the data unsorted or sorted. For example, if someone is working on a fixed set of data, she or he may choose to store the data sorted to leverage the advantage of faster data search. On the other hand, if the data is constantly being updated but rarely accessed, then storing the data elements unsorted may be a better choice. Okay, let's summarize what we have learned in this video. We have motivated a strategy of storing data elements sorted in an array. We have further introduced 4 additional operations for supporting sorted data storage. These 4 operations are inserting data at any position, accessing the first element, accessing the last element, and deleting the last element. The first data insertion operation requires a new implementation, while the other three are just special cases of the existing operations. Finally, we discussed the pros and cons of storing data unsorted or sorted. We found that if the data set is rarely modified, then we may store the data sorted for faster search. Otherwise, we may store the data unsorted for faster insertion. Alright, that's all for this video. Thank you for watching and look forward to seeing you in the next one.